So in the last lecture, we have seen what structural isomers were, right? So we'll quickly do this and we'll come to stereoisomers. So can you tell me what these two, how these two are related to each other? The first question, these two.
So they are positional isomers.
These are positional isomers of each other, okay? What about these two?
Chain isomers.
These are chain isomers. Why these are chain isomers? Because the longest chain is different, the parent chain is different, okay? Now, this is the substituent here, this methyl. Here the substituent is ethyl, okay? Now it is clear that the chain on the molecule above is 1 carbon longer than the chain on the molecule below. Can you see that?
Yes, sir.
So I am not counting because I don't want to find the name of this. So I'll just understand that because the parent chain itself is different, these are chain isomers. What about these two? So I'll separate. I'll separate the substituents. So this is a substituent. These two are substituents. I'm putting them in a different color just for understanding. And the parent chain is the yellow colored chain. Okay. Now
positional isomer.
These two have same parent chains, and the substituents are also different. Same substituents are also same. It is dimethyl. Okay. The first one will be 2, 2 dimethyl. The second one will be 2, 3 dimethyl. So only the locants are changing. The parent chain is same. The substituents are same. That's why these are
Positional isomers.
These are positional isomers of each other. What about these two?
Chain isomers, sir.
These two are chain isomers. The reason these are chain isomers,
Substituents are different.
the substituents are different. The parent chain is same, but the substituents are changing. Here, there are 2 methyl groups, which are substituents. And in the second case, there is only 1 ethyl group. Even though the parent chain is same, if the substituents are different, then they are supposed to be chain isomers of
Chain
each other.
isomers.
What
Yes,
about these two?
Positional isomers.
Positional isomer.
These are positional because only the locant is changing. This is 2, 1, 2, 3, 4, 5, 6, 7, 8 nonenol. This is 3 nonenol. Okay. What about these two?
Positional isomer.
These are again positional. What about these two?
Positional.
Chain isomers.
These are chain isomers. Okay. Be careful because the chain starts in carbonyl in aldehydes. Okay.
Yes, sir.
So one is a longer chain and one is a shorter chain. Now, if you see carefully, this thing is the substituent here. I'll put in a different color. Okay. I'll put in different pink color. Okay. This is the substituent here. Okay. Here, this is the substituent. So you can clearly see that the main chain on the upper molecule is longer than the main chain, parent chain in the molecule below. Okay. So obviously different number of carbons in the parent chain. That's why they are supposed to be chain isomers.
Chain isomers.
What about these two?
Chain isomers.
Chain isomers.
These two are also chain isomers because just like aldehyde, acid is also supposed to start at carbonyl carbon. That is this COH, the carbon which is written as COOH, that is carbonyl carbon. So obviously the substituents here are, one is methyl and one is ethyl. Can you see that?
Yes, sir.
Yes, sir.
So these are chain isomers. What about these two?
These are also chain isomers.
Chain isomers.
These are also chain isomers because even nitrile is a
Start
compound,
from the first carbon.
yeah, whose first carbon is this triple bonded carbon to nitrogen. Okay, so these are chain isomers. What about these? These are all
Chain
isomers because
isomers only.
Chain
these are
isomers, sir.
chain isomers, but they are also called
Ring isomers.
ring isomers. What about these two?
Functional isomers.
Positional isomers.
No, these are functional
Functional
isomers. Why? Because one,
Positional, both, sir.
yeah, these are actually functional isomers. Because one functional group is different. So alkene and alkyne are supposed to be different functional groups. So the one on the above is a diene and one on the below is a alkyne. So because they are different functional groups, they are functional isomers of each other. What about these two? Are these two isomers in the first place? Check.
No, sir.
No, sir, they're not isomers.
Count the number of carbons. 1, 2,
6.
Yes, sir, they're isomers.
1, 2, 3, 4, 5, 6. Here 1, 2, 3, 4, 5, 6. Number of carbons are same. Degree of unsaturation is 1 here because there is one ring. Here there is pi bond. So degree of unsaturation is 1. So both have general formula of what? C6H
1.
18. Sorry,
18.
H12. H12.
Functional isomers.
Okay,
Sir,
so
functional isomers.
these are functional isomers. Clear?
Yes, sir.
Because one is an alkane, even though it is cyclic alkane, it is still an alkane. And one is alkene. What about these three?
Functional isomers.
These are first check whether they are isomers or not. 1 carbon, 2 carbon, 3 carbon, 1 carbon, 2 carbon, 3 carbon, 1 carbon, 2 carbon, 3 carbon. All have 3 carbons.
3.
So obviously,
Yes, sir.
so these are isomers. So primary amine, secondary amine, and tertiary amine are
Tertiary amine. Functional isomers.
Functional isomers.
these are functional isomers. What about these two?
Functional isomers.
These are also functional, sir. Alcohols and ethers.
These are esters and acids.
Yes, sir. These
Functional.
are also functional.
What about these two? What are these?
These are not isomers.
Check.
Yes, sir. These are not isomers.
These are not
No,
isomers, sir.
These are isomers. See, 1 carbon, 2
1,
carbon, 3
2,
carbon, 4
3,
carbon.
4.
1,
1,
2,
2,
4.
3, 4. Yeah, isomers.
Functional isomers.
This is ketone and this is aldehyde.
Functional isomers.
So sometimes, if you just look at, glance at the molecule, it will appear as if the number of carbons are not equal. Why? Because here hydrogen is being mentioned. Okay. Here also we'll have an hydrogen. That's why this chain is appearing longer. But actually it is same as this chain. So you have to carefully count 1, 2, 3, 4. 1, 2, 3, 4. And decide whether they are isomers or not. What about these two?
Functional isomers.
Functional
Functional.
isomers, sir.
Can you name the functional groups here?
One is iron and the other.
One is cyanide. Okay, one is nitrile actually. The
1
name
is
is
nitrite.
The other is isonitrile. Okay. So
Okay,
I'll write that. This is nitrile. Nitrile ends with CN. Isonitrile ends with NC. Okay. What about these two?
Sir, they are not isomers, sir.
Just check carefully. 1
They
carbon,
are functional
two,
isomers, sir. They are functional
three.
isomers.
1, 2, 3, 4. The number of carbons are same. There is one nitrogen here. There is one nitrogen here. There is one oxygen here. There is one oxygen here. Okay. Degree of unsaturation is 1. Degree of unsaturation is 1. So obviously, automatically, number of hydrogens will also be equal. So this is an amide.
Yes, sir.
This is an acid with an amine group attached as a substituent. So these are functional isomers. Okay.
Yes, sir.
Yes.
What about these two?
Positional isomers.
No,
Positional isomers, sir.
no,
Sir, parent chain is different.
no. Just count the number of carbons. 1, 2, 3, 4,
Sir,
5,
these
6. So parent chain is this because these are ketones.
Positional, sir.
Functional isomers.
No,
Metamers.
these are metamers. So whenever you have ketone or ester or ether, two ketones, two esters or two ethers, in which the carbon that is cutting the chain into two parts, okay, this part and this part, this is cutting the chain into two parts, this part and this part, they are supposed to be metamers. Okay, these are also metamers. Why? Count the number of carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so these two are esters, so these two are also metamers. Clear?
Yeah.
These two are also
Metamers.
Metamers.
these two are also metamers, secondary amines. These are just
Yes,
like,
sir.
these are just like ethers only, but instead of oxygen, you have nitrogen. Clear?
Yes, sir.
These two are also metamers.
Yes, sir.
This is a tertiary amine. Both are tertiary amines. And the tertiary amine is sitting between this chain and cutting the chain into two parts. And if you count the number of carbons, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And 6 carbon here, 6 carbon here. So anyway, equal number of carbons. That's why they are isomers. That's why, if you classify the which kind of structural isomerism it is, it will be a metamer. Okay. What about these two? These three.
Sir,
Functional isomers.
sir,
Tautomers,
how
sir.
to identify metamers?
In metamer, there will be a functional group that will sit in between the chain. In between the chain, it will cut the chain like this. Okay. It will cut the chain into two parts. This is sitting in between the chain. This is sitting in between the chain. Here, this is sitting in between the chain. Here, this group is sitting in between the chain. Okay. Here,
Yes,
this
sir.
carbon. Whereas in positional, if you see, which page is this? Wait. Page number 7. If you look at positional isomers, this thing will not sit in between the chain, it will be attached to the chain. Okay. There is no carbonyl carbon here. A normal sp3 carbon.
Branch.
See here again. This OH is attached to the chain. It is not sitting in between the chain. There is no different carbon here. This is normal sp3 carbon only. Okay. Whereas
Yes,
if you see here, this is not an sp3 carbon. This is not an sp3 carbon. This is a carbonyl carbon. So it is dividing the chain of sp3 carbons in two parts. Okay. Here, it is dividing the chain of sp3 carbons into two parts. So here 1, 2, 3 on one side, 1, 2 on one side. Here 1, 2, 3, 4 on one side and 1 on one side. Clear? Here 1, 2 and 1, 2 on one side, 1, 2, 3 and 1 on one side. Okay. Here 1, 2,
Yes, sir.
1, 2, 1, 2, 3, 1, 2. Actually, these two are identical. I made a mistake. Clear?
Yeah, sir.
These two are identical. So we have to be careful, that's why. Because both are same, right? So they are not isomers of each other. They are not metamers of each other. They are just same.
Down also same.
Which one?
And
This
H1.
one? Okay, one thing I'll do, I'll change it. So what I'll do is, what to do, tell me?
Add one more carbon, sir.
Add one more carbon here. Add one more carbon here. Okay. Now these are metamers, right?
Yes, sir.
Check. 1, 2, 1, 2, 3, 4. 1, 2, 3, 1, 2, 3. Okay. Here also I must change. I'll add one carbon here. And add one carbon here. Okay. Now these are metamers, right?
In the down one, do you have mistake?
Here. This one, right?
Yeah, sir.
So I'll add one here. And I'll add one here. Now clear?
Yeah,
Now
sir.
corrected? Okay. What about these?
Functional isomers, sir.
No. Yeah, they are
Tautomers.
functional isomers.
Yeah.
But they are a special kind of functional isomers. These are tautomers.
Tautomers.
In fact, these are keto-enol tautomers. These are keto-enol tautomers. Now this shows tautomerism because the alpha hydrogens are available. This alpha hydrogen, one of
What
the
is
alpha hydrogen.
tautomers? Can you please tell?
Sorry.
What is
Tautomers,
tautomers, sir?
I told you in the last class now about tautomers. Whenever you have a
Yeah.
ketone,
So you told.
the ketone, the alpha hydrogen will detach from here. It will leave the electrons and detach. So these electrons will form a double bond here, and this proton will go into water. Okay. Why? Because in water some base was there. For example, OH minus base is there. That OH minus will offer electrons to this hydrogen, and it will leave because this will form a pi bond here, and these electrons will come here. Don't worry, I'll tell about that later. So basically what happens is this hydrogen will detach from here. This electrons will become what? A pi bond. The sigma bond will become pi bond, and this pi bond will become a sigma bond here, and it will attach to this hydrogen here. That's why OH is attached here. Clear?
Yes, sir,
Yeah.
got it.
Okay.
So can you
Yes.
explain just once more?
1 second. Suppose you have this double bonded. I'll show you one ketone. Suppose we have one ketone. So here you have oxygen. Okay. Now there is a hydrogen attached here. Okay. Now what happens is actually, if you take this in a basic medium, there will be a lot of OH minus ions in the basic medium. These OH minus ions will come and offer electrons to this hydrogen. Okay. So because this hydrogen got electrons from this OH minus. See, OH minus is a base. I'll come to that later when I discuss about acids and bases. A base is basically a proton acceptor. An acid is basically a proton donor. Now it is accepting a proton by offering lone pair. Okay. What will this hydrogen do?
Yes, sir.
This hydrogen, because it got electrons from this OH minus, it will leave this electrons and come out of the molecule. Okay. So basically what happens? What happens? Tell me.
Hydrogen will be
It will
removed.
break its bond.
Yeah. Okay, just let me just write. Okay. So this bond will, the sigma bond will become a pi bond. Okay. Now, why this is happening? Now, see this carbonyl carbon. Can you see the carbon to which oxygen is double bonded? It already has 4 bonds, right? This carbon,
Yes.
this carbon,
Yes, sir.
this carbon. This carbon already has 4 bonds. So if one more bond is forming, it cannot form 5 bonds, right? So what it will do? So this oxygen has already 2 lone pairs. It will make this convert this pi bond into what? It will convert
Sigma
this pi
bond.
bond. No, it will convert this pi bond into lone pair. Are you understanding?
Yes, sir.
Yeah, sir. Yeah.
So this will become a lone pair. Clear? Like this. So what will happen? What will get after this? What will get? Tell me. You'll get an enolate. You will get an enolate. How will the enolate look? Like this. See. So I'll make this into pi bond. Okay, you're understanding? And this will become a lone pair. Are you understanding? So I'll make this
Yes,
into
sir.
a different color. I'll make this orange. So there is orange color. Yeah. So this orange, I'll mention this lone pair in orange. Okay, and this will get negative charge. This oxygen. Why? Why it will get negative charge? Because here only 1 electron was with us.
Because it have extra electron.
It has 1 extra electron. Now 2 electrons are with us. That's why negative charge. Otherwise, you just see the formal charge. For looking at formal charge, you distribute the electrons. Here 1 electron, 2 electron, 3, 4, 5, 6 electrons. Okay, and oxygen is
Yes.
supposed to have. That's why it was neutral. Now count the electrons: 1, 2, 3,
7
4,
here.
5, 6, 7. So that's why
7.
negative 1. Okay. Now this is called an enolate. This is called.
Yes, sir.
Now what was this?
Enolate.
This was ketone. And what is this? Enolate. Now, what will enolate do? Will it sit just like that? It will not sit, right? And what will happen to this OH minus? OH minus will become what? Tell me. What will OH minus become after this? You have O,
O.
H. Okay, this is OH. Now, this bond pair will become lone pair, right?
Yes,
Sorry,
sir.
this
Yeah.
lone pair will become bond pair, right? And it will attach to hydrogen. Now, this will become water. You are understanding? This was hydroxide. And this is water. How did it become water?
Accepted electrons.
Hydrogen.
No, it accepted a proton. It accepted a proton. Why? How did it accept the proton? By offering a lone pair. See, it offered a lone pair. So this lone pair will become a bond pair. Okay. Now this hydrogen will be neutral, obviously, because it had 1 electron here. Now also it has 1 electron. Now this OH minus was negative. Why it was negative? Because it had 1, 2, 3, 4, 5, 6. Here, if I draw this like this.
7. 1 extra
7
electron.
electrons. 7 electrons. 1, 2, 3, 4, 5, 6, 7 electrons. Here, 1, 2, 3, 4,
6
5,
only.
6 electrons. So that's why it is water. Clear?
Neutral. Yeah.
Okay. Now this reaction is base catalyzed. This reaction is base catalyzed. Catalyzed means what? What do you mean by catalyzed?
Increase the speed of reaction.
Increases speed of reaction, but the catalyst itself doesn't participate in reaction. Okay. That means this OH minus that was consumed, I should get back, right? because it shouldn't participate in reaction. That OH minus is a catalyst. Okay. So overall in the net reaction, it should not be consumed. So what will happen? This enolate, it will offer the lone pair to that proton again. And it doesn't need to be this water, some other water molecule also, it can be. You are getting my point? See, that water molecule will go somewhere. But this reaction is happening in water, so it will take another water molecule. Clear?
Yes, sir. Yes.
So what will happen? What will happen? Tell me. This will become, so I'll put in red. This will become OH, clear? Plus,
Yeah.
what will it?
OH
What will
minus.
this become? This will become OH minus. Clear?
Yes, sir.
So one OH minus consumed and one OH minus regenerated. Clear?
Yes, sir.
So overall, what happened in this reaction? This ketone converted into enol. Converted into enol.
Enol.
And this is a base catalyzed reaction. This is a base catalyzed reaction. Are you understanding?
Yes, sir.
And there will be acid catalyzed reaction also, but I'm not going into that now. Once we start this resonance and all those things, these reaction mechanisms will be easy for you. That's why I'm not going into that. The only thing you have to remember is for something to show,
Sir, the
tautomerism.
meeting might end.
Okay, I'll restart. So you're understanding my
No,
point?
sir. It's not an ending notification, sir. It says that we have unlimited time.
Okay, fine. So for tautomerism, what do we need? We need alpha hydrogen. We need alpha hydrogen. Clear?
Alpha hydrogen.
Now
Yes, sir.
these two are also tautomers. These two are also
Tautomers.
tautomers. Okay? Clear?
Yes, sir.
And one more thing you just keep in mind, in a basic reaction, okay, you should never get a positive charge in anywhere in between the mechanism. The thing I wrote is a mechanism here. So you see all charges are negative charges. There is no positive charge anywhere. Can you see that?
Yes, sir.
And in an acid catalyzed reaction, you should never get a negative charge.
Negative
anywhere.
charge.
You should always get a positive charge. And I'll show you later how to write mechanisms for reactions. This is just for understanding I have written, but don't worry. After some time, after going through some topics, you'll become expert in these kinds of reactions. Clear?
Okay, sir.
Okay. Now let us go to next isomerism, which is
Stereoisomerism.
stereoisomerism. In stereoisomerism, so basically, we have seen all the structural isomers. In stereoisomers, there are two big topics. One is geometric isomerism and the other is optical isomerism. So optical isomerism, I will deal with that later after dealing with geometric isomerism. Okay. Now, before going into isomerism, let us just see how sp3 carbon is. So sp3 carbon has 4 bonds, and those 4 bonds are, arranged such that the ends of those 4 bonds are vertices of a tetrahedron. You know what tetrahedron is? This.
Yes,
Okay.
sir.
And the angle between any two bonds attached to carbon will be 109 degrees 28 minutes. Okay. And I'll prove this in some time. Just remember. Clear? So
Okay,
how
sir.
many sp3 bonds does a carbon have? 4 sp3 bonds. Okay. Why? Because before hybridization, 1 s orbital and 3 p orbitals combine to form equal number of hybrid orbitals, which are 4 sp3 orbitals. Okay, so this is one sp3 orbital, this is another sp3 orbital, this is another sp3 orbital, this is another sp3 orbital. Clear?
Yes, sir.
Okay. Now this is how a
Yes, sir.
tetrahedron looks. So this is the tetrahedron. These are the vertices of tetrahedron. So the atoms or groups of atoms attached to carbon will be on the vertices of tetrahedrons, and carbon will sit in the center of tetrahedron. Clear? Okay.
Yes, sir.
Now, how to understand a tetrahedron? If you take a cube, cube has 8 corners, right? Cube has 8 corners.
8 corners.
And if you take 4 of the 8 corners such that no 2 corners have a common edge, then those 4 corners will be the vertices of tetrahedrons. Okay? Clear? See,
Yes,
this
sir.
is a cube. I have taken this corner. I left the neighboring corners because they have common edge. Okay? Then I
Yeah,
took
yes,
this.
sir. Got it.
I left the neighbor, this neighbor and this, the other neighbor. And I took this. I left the neighbor. I took this. So its neighbors are already left. So these corners will be the corners of a tetrahedron. Do you agree?
Yes, sir.
Okay. Now, if I take the 4 corners of tetrahedron and the center, and if the side of the cube is A, what will be the positional vectors of these points? What about O? What will be the coordinates of O? It will be 0, 0, 0. Agreed? Okay? Following.
Yes, sir.
What about point P?
Yes, sir.
It will be A, 0. Are you understanding? Because z-axis is it is not along z direction, and it is, you know, A in the x direction, A in the y direction, and 0 in the z direction. Are you understanding?
Yes, sir.
What about this? It will be 0, A. Agreed?
Yes, sir.
What about this? A, 0, A. Correct? And what about the point at the center? It will be A by 2, A by 2, A by 2. Do you agree? Clear? Why you know?
Yes, sir.
Yes.
Because this is 0, 0, and this corner is A, A. That is the body diagonal, and it will be at the center of the body diagonal. That's why the coordinate of the center of this will be A by 2, A by 2, A by 2. Clear?
Yes, sir.
Now,
Yes.
suppose I need to find the angle between, see, here carbon sits, right? Here one bond, here one bond, here one bond, and here one bond. Do you agree?
Yes, sir.
So suppose I want to find the angle between any 2 bonds. What should I do? I should find the vector of this. I should find the vector of this. Okay? And I have to find the angle between the vectors using, dot product. Clear?
Yes, sir.
A bar dot B bar by magnitude of A bar into magnitude of
B bar.
is equal to cos theta. I can use this formula. Correct?
Yes, sir.
Now, see, I'll take any 2. So this has position vector this has position vector this has position vector this has position vector this, which I already told you. Clear?
Yes, sir.
Now, what about the vector OS? So OS is what? This is O and this is S. So OS is this. This is OS, right? So OS is S minus O. Okay, vector S minus vector O. So what will it be? A by 2 I cap plus A by 2 J cap plus A by 2 K cap minus 0 I cap, 0 J cap, 0 K cap. So what will you get?
A by 2 I cap plus A by 2 J cap plus A by 2 K cap.
A by 2 K cap. Correct? Next,
Yes, sir.
take another vector RS. What about RS? This is R and this is S. So RS is vector R minus vector S, right?
Yes, sir.
Or vector S minus
Yes,
vector R. What will you get? This minus this, minus A by 2. This minus this is A by 2. This minus this is minus A by 2. Correct?
Yes, sir.
Yes, sir.
RS. So RS. So let me write down SR. So SR is vector R bar minus S bar. So R bar minus S bar is what? A minus A by 2, 0 minus A by 2, A
Minus
A
A by 2. A by 2.
So A by 2 minus A by 2,
Minus A by 2.
Clear?
A by 2. Yes, sir.
By 2 minus A by 2, A by 2. Now what is the dot product of these two? These two will be minus A square by 4. These two will be minus A square by 4. These two will be plus A square by 4. This plus A by 4 minus A square by 4 will cancel. So minus A square by 4 will be present. Minus A square by 4 in the numerator. In the denominator, what is the magnitude of this? A by 2 into root 3. What is the magnitude of this? A by 2 into root 3, correct? And in the denominator, it is minus A square by 4. So what will you get? A square by 4, A square by 4 will cancel. And what will remain? Minus 1 by 3. Clear?
1 by 3. Yes, sir.
Minus 1 by 3.
Yes,
Okay.
sir. Got it.
See, dot product is easy, amma. Minus A square by 4 plus A square by 4 minus A square by 4.
Minus
Okay.
A square by 4.
Minus A square by 4 plus A square by 4 cancel. So what will remain? Minus A square by 4
Minus
will
A
remain
square by 4.
in the numerator. Here, this one.
Yes, sir.
Okay. What about denominator? It is the magnitude of first vector, which is A by 2 into root 3 into magnitude of second vector, which is A by 2 into root 3. Correct?
Yes, sir.
This into this is A square by 4. So these two will cancel. Minus 1 will remain. And root 3 into root 3 is 3. So how much? Minus 1 by 3 will remain. Clear? So theta is cos inverse of minus 1 by 3. Do you agree? Okay.
Yes, sir.
So what is cos inverse of minus 1 by 3? Let us see. Cos inverse. So where is cos inverse? Cos inverse of minus 1 by 3. Minus 1 divided by 3. 109.5. Can you see that?
Yes, sir.
Yeah. 109.5. So it is 109 degrees, 30 minutes approximately, correct? 0.5 degrees is 30 minutes. Na?
Yes.
But if you see
Yeah,
precisely, it will be 28 minutes. So
Yes,
theta
sir.
is 109 degrees, 28 minutes. Clear?
Yes, sir.
Okay, this was the difficult part. So this angle will be 109 degrees, 28 minutes. Any angle, this angle, any angle will be 109 degrees, 28 minutes. If you
28
want, you can-
minutes.
Okay.
Okay, sir.
What about sp2 carbon? sp2 carbon is a trigonal planar structure. Carbon will be at center and
120 degrees.
three bonds will be in a plane and this angle will be 120 degrees. The angle between these two will be 240 if you go from this side. If you go from this side, it will be 120. Okay. So
Yes, sir.
maximum angle will be 240 and minimum angle will be 120 between any two bonds. Okay.
Yes, sir.
So basically, these three groups will sit on the corners of a
Triangle.
equilateral triangle. Clear? Okay.
Yes, sir.
What about sp carbon? It will be linear. An angle between
180,
the bonds
180.
180 degrees. Clear?
Yeah.
Okay. And in sp orbital, 50% s character, 50% p character. In sp2, 33% s
33,
character,
67.
p character. In sp3, 25% s character and 75% p character. Why? Because it is obvious.
Yes,
Okay.
sir.
Here it is 50-50. Here it is 1:2. Here it is 1:3.
1:3.
Okay.
Yeah.
Now that means sp orbital will be little bit shorter Why? Because S character is more. sp2 will be longer, sp3 will be the longest. You
Yeah.
know why? The character of P is what? The double shape, right? And character of S is what? Tell me.
Circle.
Spherical, spherical.
Spherical.
That's why the SP, this will be short and sp3 will be long. Are you understanding my point?
Yes.
Yes, sir.
So SP will be something like this. SP will be something like this. Okay. What about sp2?
Two dumbbells and one sphere.
Larger.
sp2. I'm talking about one sp2 orbital. I'm talking about one
It will be
sp2
larger
orbital.
than SP.
Longer, not larger. It will be longer.
Longer.
What about sp3? It will be the longest.
Longest.
And it will be the thinnest also. And this will be the thickest also.
Boldest.
Okay. So SP will be like this, sp2 will be like this, sp3 will be like this. And it is very important to remember this because later when you, do the rankings for acid strength and basic strength, this concepts will be useful. Okay.
Okay, sir.
Okay. Okay. Now, basically, generally, two sp2 orbitals are two sp orbitals are present together. 3 sp2 orbitals are present together, and 4 sp3 orbitals are present.
4 sp3.
Okay. Okay. Now, first we'll go
Together.
into geometric isomerism. Now, geometric isomerism is shown in various situations, but the most simplest situation is alkenes. In alkenes, okay. Now, whenever you have alkenes, see here, I have two alkenes. The first condition for something to show geometrical isomerism is the double bonded carbon. So these two are double bonded carbons, right?
Yeah.
Both the double bonded carbons must have two different groups or atoms attached to each. You are getting my point?
Yes, sir.
That means none of the double bonded carbons can have same groups attached if it should show geometric isomerism. For example, if you look at this molecule, this carbon has two same groups attached. This carbon has two different
Yes,
groups.
sir.
But because one carbon has two same groups attached, this does not show geometrical isomerism. Correct?
Geometric isomerism.
Okay.
Yeah.
No geometric isomerism is possible. Here
also, sir, two methyl groups are attached. Same. So
here
no
two methyl
geometric
groups are
isomerism.
attached. So here no geometrical isomerism, okay, is not possible. Clear?
Yes, sir.
So I have mentioned in red circles the reason why geometrical isomerism is not possible. Clear? If the
Yes,
above
sir.
condition is not met, then the molecule must exhibit geometrical isomerism. Okay? Now, here,
Okay.
if you look at this double bonded carbon, two different groups are attached. This double bonded carbon, two different groups are attached. That means this shows geometric isomerism. Okay?
Yeah, yeah.
Clear? Here also, see,
Yes.
two different groups are attached. Here, two different groups are attached. In fact, these two are structurally same. Do you agree? What
Yes,
do you
sir.
mean by
CH3 is
see, formula is same. That is an old story. We have seen that. But structurally also they are same. What do you mean by structurally same? This carbon has one H group and one CH3 group attached. This carbon has one CH3 group and one H group attached. Clear? This carbon has one CH3 group and one H group attached. This carbon has one CH3 group and one H group attached. Are you following?
one H group attached.
Okay. Now the problem
Yeah, sir,
is,
following.
see, even though the connections are same, the orientations of the molecules are different. What do you mean by orientations are different? Here CH3 are facing in
At
the
one-
opposite directions. Here CH3 are on, the same side of this double bonded.
Same direction. Same
clear?
side.
Now the problem is, see, this is a sigma bond and another is a pi bond, right? So how is a sigma bond? Sigma bond is present between carbons, and pi bond is present in the form of a banana at the top and banana at the bottom. Clear? These are pi electron clouds you have seen in chemical bonding. Clear? Are you understanding?
Yes. Sir.
Yes, sir.
Suppose we have two carbons. I'll just take this. So suppose these two carbons are there. What do you mean by this? This is actually like this. So this is actually like this. The sigma bond is present in between. Okay. So I'm drawing the sigma bond, and pi bond is something like this. There is a electron cloud above like this, and there is an electron cloud below. This is one, and this is another. Now suppose if you try to rotate this carbon-carbon bond, it cannot rotate, because in order to rotate, these two bridges must break. Clear? That means this molecule is locked in this orientation. You are getting my point?
Yes, sir.
No
Sir, if there is
free.
only one pi bond, why are you drawing two?
No. One pi bond is one above and one below. Two pi bonds are there, then one will be at front and one will be at back also. For example, if you have triple bond, two pi bonds are present, right? Okay. So see, this is one only. This is only one pi bond. If triple bond is there, one will be at front and one will be at back. You are getting my point?
Yes, sir.
I'll show you. Don't worry. So I'll show you. Now let me show you one thing. If you have a single bond, let me just wait. If you have a single bond like this, what is this molecule? Tell me.
Ethane molecule.
Ethane molecule, right? Now, if you look at this molecule in 3D, it will be like this. Can you see?
Yes,
These
sir.
two,
Yeah.
these two are carbons, gray colored, and white colored are hydrogens. And there is a bond between two carbons. Can you see? And
Yes, sir.
that bond can be rotated. That bond can be rotated because it is a single bond. That means you are getting my point.
Yes, sir. Yeah, got it.
These hydrogens, now they are in the staggered position. They can come in eclipse position also. Huh? Okay.
In skew position also.
Yeah. So
Yeah.
they can rotate. Okay. But if you have a double bond, if you have a double bond, for example, okay, let me just take this. I'll put a double bond in between. So this is your what molecule is this?
They can't rotate,
Ethene.
sir.
Huh?
They can't
So-
rotate if double bond is there.
They can't rotate. I'll show you why. I hope it will show you. So see, how can they rotate? Tell me. Can they rotate?
Yes, sir. They not.
If you rotate them, what will happen? That will break, na?
No.
If single bond is there, you can rotate. If
Yeah.
you imagine a 3D model made of plastic, if you try to rotate this, it should break, right? And one more thing, everything is in plane. See, in one plane here. See,
Yes, sir.
because it is trigonal planar. Okay. sp2 carbon, right?
Yeah. Yeah.
And actually, how these are present is one electron cloud is above and one electron cloud is below. Okay. Okay. Anyway, triple bond also cannot rotate. But triple bond, there is no use now. So anyway, we'll see. So this is acetylene, right?
Yeah. Ethine.
So if you look at this, the 3D structure of this, it will be like this. This also cannot rotate. See, and it is linear. Can you see?
Yeah, sir. Only in one plane.
Only on one line actually. Okay,
Yeah, yeah.
clear? So even this
Yes, sir.
triple bond also cannot rotate. Okay.
Yeah.
Okay, fine. So anyway, these cannot rotate. That's why these two will be always opposite. Here, these two will be always on the same side. Okay. So these two are, see, connections are same, but orientations are different. Orientations are different. So these are not structural isomers of each other because they are structurally identical, but orientations are different. That's why they are geometrical isomers. Clear?
Yes, sir.
What about these two?
Which two, sir?
These two.
They draw geometrical isomers.
They are also geometrical isomers only. Okay. Chlorine, chlorine. Okay. CH3, CH. This is same, but on this side we have same groups attached, but on the opposite sides. On the opposite side. So these two are also geometrical isomers of each other. What about these two?
They too are geometrical, sir.
They two are because this is same. This is just opposite. Clear? So these two are also geometrical isomers of each other. Clear?
Yes, sir.
Now, does this show geometrical isomerism?
They are not isomers actually.
Yes,
No, no,
sir.
no.
They can't
Can this
show.
show? Can this show geometrical isomer? My question is, can this have a
No,
geometrical isomer?
No, sir.
No,
Cannot
sir.
have. It cannot have. Can this
No,
have
no,
a
sir.
geometrical isomer?
No,
Okay. Can this have a geometrical isomer?
no, sir.
No.
No. No. No. Can this have a geometrical isomer?
No,
No.
again.
No.
Why? Because you check only one thing. If any carbon has two same groups, no. Two
Yes,
same
sir.
groups, no.
No.
Two same groups, no. Two same groups, no. Simple.
No.
Okay. Okay, fine. What about these two?
So they can
First,
show.
let us divide these into.
They
First, let
can
us give
show.
them names. Yeah, these two are actually geometrical isomers of each other. Okay. Now, when we have geometrical isomers, we can give them a designation. Okay. We can name them either cis or trans. But for naming cis or trans, there is a condition. On the neighboring carbons, there must be at least one same group attached. Okay. On this carbon, there is a CH3 group. On this carbon, there is a CH3 group. On this carbon, there is a hydrogen. On this carbon also, there is a hydrogen. That means we can name them as cis and trans. Clear?
Yes, sir.
If the same groups on neighboring atoms are on same side, then that is cis isomer. If same groups on neighboring atoms are on opposite side, then it is a trans isomer. Clear?
Trans isomer.
Yes, sir.
Are you understanding?
Sir, at least one should have same or both should have same.
At least one. At least one. For example, here. Here, see.
Okay, okay.
Here, this carbon has hydrogen, this carbon has chlorine. These two are not same. This has hydrogen and this has chlorine.
But
Not same, not same. But I'm not worried because at least one is same, na?
yeah, yeah.
So
Yes,
this
sir,
is
yeah.
cis and this is trans. Clear?
Trans.
Okay. What
Yes,
about
sir.
these two?
First
Trans.
one is trans and second one is cis.
Second one is cis. Okay. What about this?
Yeah.
Trans.
Same. Trans and cis.
This is trans and this is
This is
cis. Clear? What about this?
yes, sir. Sir, no trans and no cis.
No trans, no
No
cis. But this shows geometrical isomerism. Okay. Why geometrical isomerism? Because this carbon has no same groups attached. This carbon also has no same groups attached. This carbon has no same groups attached. This carbon also has no same groups attached. So these
Yes, sir,
two
yeah.
show geometrical isomerism, but they cannot be designated as cis and trans.
Cis and trans.
Yeah.
Yeah.
Okay. So for these kinds of
Yes, sir.
molecules, we'll design a different method of giving them names. Okay.
Okay.
Okay. For geometric isomerism to exist, there must be no common group on the same carbon. Clear? So here also no
Yeah.
same, no common group. Here also no common group. No common group, no common group. That means these must show geometrical isomerism. Clear? But this
Yeah.
cannot be named cis and trans. Okay? Okay. Clear?
Yes, sir.
So what to do in these kinds of cases? For that, we will learn one thing which is called Kahn-Ingold prelog. And this is important because the same thing will be used in stereoisomerism. The same method will be applied in stereoisomerism. So it is a very important topic. So Kahn-Ingold prelog. So two scientists named, one is Kahn and one is Ingold. They invented this technique of dealing with stereoisomerism and geometrical isomerism. So in Kahn-Ingold prelog, what you do is you give priority to the groups or atoms attached to carbon. Okay, clear? Now
Yeah.
suppose you have an sp3 carbon. How many groups are attached? 1, 2,
Four.
3, 4. So for the 4 groups, you will give ranking, and that 4 groups must be different. Okay, for example. And how the ranking is given? Ranking is based on atomic number. Ranking is based on atomic number.
Atomic number.
For example, here one hydrogen is attached, one chlorine is attached, one carbon is attached, and one fluorine is attached. So the atom or group with the highest atomic number will get the first rank. So here chlorine will get first rank. Then comes fluorine. That's why fluorine will get second rank. Then comes carbon. Carbon will get third rank. Then comes hydrogen. Hydrogen will get fourth rank. Are you understanding?
Yes, sir.
Okay, that is
But sir,
Kahn-Ingold
in
prelog.
methyl group, hydrogens are also present now.
No. First
We
look
should not
at
consider
the
them.
first look at the carbon atom to which the bond is attached.
Okay.
If
Got
that
it.
clashes, then go for the next atom.
Okay.
Okay. For example, on sp2 carbon, only 2 groups are attached, so there will be only 2 ranks. One is CH3 first rank, one is hydrogen second rank. Here CH3 first rank and hydrogen second rank. Clear?
Yeah.
You don't consider double bonded group. Okay, so forget this. So this group for this carbon is ignored. So only 1 group and 2 group, single bonded. Okay, here
Yes, sir.
this is first rank, this is second rank for this carbon. For this carbon, this is first rank and this is second rank. Clear?
Yes, sir.
Okay. Now, what about this? These groups, one is CH3 group, one is COOH group, one is CHO group, and one CH2OH group. Now the problem is all are carbons only. Okay, carbon, 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 carbon. So clash, right? Okay.
Yeah.
Now I must go to the next atom.
We should
So here this carbon is
we should
attached
follow
to
the priority list.
priority. Okay. So next, this carbon is attached to how many oxygens?
2 oxygens.
Actually 3 oxygens if you go by the rule, because the COH group will be like this. Okay, COH group is this, right? So it is attached to 1 oxygen, 2 oxygens, 3 oxygens.
Oh,
Because
yeah.
three bonds. Okay, so that comes first. Then comes CHO
Yes,
because
sir.
it is attached to 2 oxygens.
2 oxygens.
Then comes alcohol because it is attached to 1 oxygen. Okay,
Yes, sir.
so this is the first rank, this is second rank, this is third rank, and this is fourth rank, because
Fourth
this is
rank.
not attached to any oxygen. Clear?
Any oxygen. Yeah.
Okay. What about this? What did I give number 1 as? Fluorine. Correct? Why? Because this is attached to carbon, this is attached to carbon, this is also attached to
Yeah.
carbon. Don't worry about group, because it comes next. What is first attached, that is important. Okay. Carbon, 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 and fluorine. Who will win?
Fluorine.
Fluorine. It got first rank. Okay. Now, Because carbon has clashed, then go for the next. So here this carbon is
Br,
attached to
bromine.
this carbon is attached to oxygen. This carbon is not attached to anything except hydrogen. So who will win? Bromine.
Bromine.
So this will get second
So
rank.
second rank.
So this carbon is attached to oxygen. This carbon is not attached to oxygen. It is attached to hydrogen. That's why it will get the third rank and this will get the fourth rank. Clear?
Yes, sir.
So this is how we give rankings for Khan Ingold pre-log. Clear? And we'll come back to this
Yes, sir.
carbon because when we study optical isomerism, it is a very big topic. So there we will see R and S configuration. We will see there. But now we are studying geometrical isomerism. Let us come back to geometrical isomerism. Now here, 4 different groups are attached. So the problem is I cannot give cis and trans to this. So what I'll give? I'll give the priority. This will get number 1 and this will get number 2. I'm talking about this carbon, correct?
Yes, sir.
What about this carbon? This will get number 1. because it is
NH2
chlorine.
one.
NH2
Yeah,
will
yeah, yeah.
get.
Sorry.
Yeah. Okay.
Number 2.
What about
yeah.
this? 1, 2 for this carbon.
CH2 2, yeah.
For this carbon,
1 and
1, 2. Clear?
2.
Now,
Yes,
if
sir.
one is on same side, one is on same side, then that configuration is Z isomer. Okay. If one is on the opposite
Yeah.
side, then it is called E. Okay.
Okay,
So
sir.
these are actually some German origin. The full form of this Z and E, I don't remember. No need to
Some
remember.
and
You just remember that Z is on the same side and E is on the opposite side. Clear?
okay, sir.
Okay, fine. What
Yeah.
about this? What about this?
It is Z.
It is Z and it can
Yeah.
also have cis and trans, right?
Yeah, sir. Yeah. It is cis and
It is also cis. It is also
cis. Sir, it will not have Z then. Anyhow, it has 2 same carbons, no?
see Z and E. It is present always. Okay. Whenever you have
Okay.
geometrical isomerism, you will definitely have Z and E.
Okay, okay.
But you may have cis and trans or may not have cis and trans.
Yeah, sir. Got it.
Got it?
Yeah.
Now what about this? E.
E,
And it is
trans.
trans. Now can you guess something?
Got, sir.
Is cis always Z and trans always E?
Yeah.
Is cis always E and trans always E?
Yeah, sir. Cis will be Z and trans will be E.
Actually not true. I'll show you. This one. Can you see it is E? Because number 1 priority
it
is
is
this,
E.
number 2 is this here for this carbon. For this carbon, number 1 is this, number
Yeah,
2
yeah.
is this. So 1 is on the opposite side, it is E. Here. Number 1 and number 2 for
Okay.
this carbon. For this carbon, number 1 and number 2.
Number
1
1
is
and
on
number
the
2.
same side.
Same.
So, so E is
E and
trans
cis.
and E is trans and G is cis. Okay, fine.
Yeah.
Not a problem. What about this? Here,
It
number
is
1 is
trans.
this. Number 1 is this. Number 2 is this. Here,
Yeah,
number
yes,
1
I
is
got
this
it.
and number 2 is this. Correct?
So it is Z, yeah.
It is Z, but because
But it
same
is
groups are
trans.
on the opposite side, it is trans. Okay.
Yeah.
Here, this is number 1 and this is number 2 for this carbon. For this carbon, this
Methyl
is
is
number 1 and this is number
hydrogen
2. One is on the opposite side, that's why it is E. But because same groups are on the same side, it is cis.
cis and
Clear?
E.
So Z can be trans also, E can be
Yes,
cis
sir.
also.
Yeah.
Clear? What about this?
Yeah, sir. Yeah, sir.
What about this? Number 1 and number 2. Number 1 and number 2.
No cis trans.
So this is Z
Z.
because on the same side. Okay? Clear?
Yes,
What
sir.
about this?
Yeah.
Number 1 and number
Number
2
1
for this
chlorine and
carbon.
number 2 fluorine.
Number 1 and number 2 for this. 1 and 1 are on the
Number and one.
opposite side. That's why it is E. Clear? And what about cis
E.
and trans? They
Yeah.
don't exist. They don't exist. Cis and trans,
They don't
They
have
don't?
same carbons. Same molecules.
have same
They don't
groups.
have.
same groups or
Sorry,
same
sorry, yeah.
atoms. Okay. Clear? So these cannot exhibit cis and
Yes,
trans.
sir.
But whenever you have geometrical
Yeah.
isomerism, you will always have E and G. You will always have E and G. You
Yeah.
may or may not have
E and
cis and
G.
trans. Okay. And Z can be
Yeah, sir,
trans,
yeah.
Z can be cis, E can be trans, E can be cis. Okay. All those things I have
Yeah.
written here.
Yeah.
Okay.
Got it, sir.
What about this?
It is
It does not.
trans.
It does not exhibit geometrical isomerism. You know why?
Yeah, sir. Same
Same
group on carbon. Same two groups, yeah.
For this carbon, same two groups. So no
Yeah, yes,
geometric. Okay.
Yes, sir.
What about this? No. Why? Same groups. Clear?
They do know, sir.
Yes, sir.
Same hydrogens, yeah.
It doesn't matter.
Yeah.
This has different groups. If any carbon has same groups, then it doesn't exhibit geometric isomerism.
Geometric
Clear?
isomerism. Yes, sir.
What about this? Number 1, number 2. Number 1, number 2. So on same side, that's why E. And same groups are also on the same side, that's why it is cis. Clear?
Yes,
They are on
sir.
opposite side, that's why trans. Number 1, number 2.
Yes,
Number
sir.
1, number 2. So number 1 is on
E.
the opposite side, that's why it is E. Clear?
Yes, sir.
What about this?
Trans and Z.
Number 1, number 2. Number 1, number 2. So this is Z.
And trans.
And same groups are on opposite side, that's why it is trans. Clear?
Yes, sir.
Yes, sir.
What about this? Number 1, number 2. What about this?
Cis and E.
Number 1. So this is E. But same groups are on same side, that's why it is cis. Clear?
Yes, sir.
Yes, sir.
What about this? Number 1, number 2. Number 1, number
Z.
2.
No
This
cis
is
and
Z.
trans.
No cis and trans because no same groups are attached. Clear?
Yeah, yeah.
What about this? Number 1, number 2. Number 1, number 2.
Number 1,
So
number
one is on opposite side, that's why it is
E.
Clear?
E.
Okay. Now, whenever you have, one double bond or 3 double bonds or 5 double bonds,
5.
odd,
Yeah, yeah. 1,
consecutive
3,
double
5, 7,
bonds,
9.
they may show geometric isomerism. They may show. Okay. When they will show? When obviously 2 different groups are attached here, 2 different groups are attached here. Clear?
Yeah.
Whenever you have even number of double bonds, 2, 4, 6,
6.
this will not show geometrical isomerism. The reason is this. I just told you that pi bonds are like this, right?
Yeah.
So if pi bonds are like this in between these 2 carbons, on the neighboring carbon, the pi bonds will be like this. Okay. So this is top and
Yeah.
bottom. This is top and bottom. In neighboring, double bond will be at front and back. You know why? Inter-electronic repulsions, they will not be on the same plane. Clear? They will try to move farthest from each other. So if this is on top and bottom, this pi bond will be at the back and front. Because if both are on top and bottom, there will be repulsion between the 2 neighbors. Clear?
Yes, sir.
What about the other? It will be on top and bottom again. Why? Because the neighboring is on front and back. Clear?
Yes, sir.
So when this happens, this will be in this plane. Because this should be planar, right? Trigonal planar. This is sp2 carbon. Okay?
Yeah.
And this is sp. Why? Because it is double bonded here. So forget about this. This is sp. This is sp2.
sp carbon.
So these 2 bonds will be in
Yeah.
the. That means
Again.
these 4 bonds will be in the same plane. Clear?
Yeah.
If you have 1 double bond, 3 double bond, 5 double bonds, clear? Whereas if you have even number of double bonds, then what will happen? This will be at top and bottom. So this will be at top and bottom.
Front and
Okay.
back.
This will be at front and back. So this carbon's plane will also be like this. Okay. So this will be at front and back. Clear? Now, when
Yes,
these two
sir.
bonds are at top and bottom and these two are on front and back, this is in this plane, this is in this plane. Clear? So these cannot
They are
show
not trigonal
geometrical
planar.
No, no, no. Which one? Which one? This is trigonal planar. This is trigonal planar. But this is in this plane. This is in this plane. You are understanding?
Yeah, yeah,
This,
sir.
this is in this plane. This carbons, this bond, this bond, this bond, this bond. Whereas this is in this plane. This bond, this bond, and this bond. Why? Because of the electronic repulsions between these two. These, pi bonds are at top and bottom. These are at front and back. If these are at front and
Front
back,
and
these will
back.
also
Yeah, sir.
okay. That means we cannot
and
have
back.
cis and trans and Z and E here, even if different groups are
Yeah,
attached.
yeah.
So if you have even number
Okay.
of consecutive double bonds, we cannot have geometrical isomerism. Clear?
Yes, sir. Got it.
Same thing for spiro compounds with rings. So if you have even number of these things, what? Even number of
Carbons.
rings, 2 rings,
Double bonds or rings. Yeah.
4 rings.
4 rings.
Okay, so these cannot exhibit geometric isomerism because one ring will be like this, another ring will be like this, because this is which carbon? 3 carbon, right? sp3 means what? Tetrahedral, right? Tetrahedral means 2 will be in one plane, one will be at front and one will be at back. Clear? So this ring will be like this.
Yeah, yeah.
Whereas here one will be at front and one will be at back. This is already at back and front. That's why what will be here?
They will be in one plane.
Top and bottom. So that means
Yeah.
this will be in this plane. These two will be in this plane. So they cannot exhibit what? Geometric isomerism. Clear? Are you understanding?
Yes, sir.
Okay.
Yeah,
Whenever
they
you
can
have
exhibit.
even number of rings, just like
They
even
cannot
number of
exhibit geometrical isomerism.
they cannot exhibit geometrical isomerism. When you have odd number of rings, they exhibit geometrical isomerism. Why? Because
Yes,
look at
sir.
this. One will be like this. One will be like this. One will be like this. This and this will lie
Yes,
in the
sir.
same plane.
Yeah. First and
Yeah.
last will lie in same plane.
Yes. That's why they can have cis and trans. When these two groups are different and these two groups are different, they may show cis and trans, but they will definitely show Z and E.
E and Z. Yeah.
E and Z they will definitely show. If
Yes, sir.
these two groups are different and these two groups are different. And after this, if these two groups are same, then obviously there will be no geometrical isomerism. Clear?
Yeah, yeah.
But here it doesn't matter. Even if you have same groups or different groups, whatever you do, this will never show geometrical
Geometrical
isomerism. Clear?
isomerism. Because they are on different plane.
Yes. What about this combination of double bond and rings? Okay. So if you have 3, then
They can
odd
show.
number, they can show. 3, they can show. Clear?
Yes, sir.
1, 2, 3, 4, 5, they can show.
They can show.
Clear? Whenever you have
Yes, sir.
even number,
No, they cannot show.
3, 4, 1, 2, 3, 4, they cannot show. So this will not show geometrical isomerism. This will not show geometrical isomerism. This will not show geometrical isomerism. Clear? The reason is again
Yes,
same.
sir.
Okay.
Even numbers.
Okay. Now tomorrow I'll continue geometrical isomerism only, but a different situation. Okay. So we'll consider geometrical isomerism for cycloalkanes tomorrow. Okay.
Okay, sir.
So I'll share this. Just go through carefully. Read carefully. Okay. Tomorrow I'll continue with geometrical isomerism for cycloalkanes. After that, we'll start one big topic, which is optical isomerism.
Okay, sir.
That optical isomerism is a big topic and very important topic also.
Okay.
Okay, tomorrow we'll continue.
Allah Hafiz.
Okay.